can even set it up with, I've got a power supply here, I have a switch. I shut the switch down, I charge up the capacitor, I now break the switch, and so this is no longer a part of the circuit. This is no longer part of the circuit because there's no path there's a break in the path. And so what I have now is just this. So this is fully charged and the power is going to start to drain. I got a bunch of electrons here, excess protons here. And so now the electrons are going to start to flow around like this, or the current's going to flow around like this. So this is my charge flowing and this is my current. Well, Kirchhoff again. I start someplace and I work my way around. Doesn't matter where I start, but I'm going to start here and I'm going to go in the direction of current. As I go from the negative to positive plate across the capacitor, gain potential or lose potential?
Lose potential.
Going from negative to positive? That mean you're changing your mind? Or so this is the voltage loop I'm taking right here. If I go from a negative plate to positive plate, gain potential or lose potential?
Gain.
Yeah. When I go from negative to positive, I gain. So I have some potential across the capacitor, and then I'm going to have to lose it across here because I have only two components. So minus the potential across the resistor, potential difference is equal to 0. Across the capacitor, I know that is the charge on the capacitor divided by the capacitance, minus this is the current flowing across the resistor times the resistance. Now notice, I have them I have subscripts here. Because this is the charge on the capacitor, this is the current that comes from the charge that's off the capacitor. So QC plus the charge flowing across the resistor is equal to some constant. So if I take the derivative, QC plus QI, actually it should be R, is equal to 0. So QC dot is equal to negative QR dot. The dot being derivative with respect to time. So this I right here is dq dt, the Q that's going across the resistor, so I have QC over C minus dqr dt times R. I know from this is QC over C plus dqc dt R equals 0. QC over C equals negative dq, let's stick the R in front, negative R dq dt. It's a simpler first order differential equation. I don't have to do U substitution at least. So I end up with QC over, wait, no, wrong way. On the left-hand side, I have negative 1 over RC dt. And that's going to be equal to dqc over QC. Integrate that whole bit. So I have negative T over tau still, using the same time constant, is equal to the natural log of Q. So Q, as a function of time, is e to the negative T over tau. And so we have this exponential decay. It's not all of a sudden. And in theory, you could be able to actually measure this in lab. It's not quite so simple in practice. If I break a switch too slowly, it's gonna spark and I'm gonna lose some charge off of this. So I need to break it quickly. And it's very difficult to break the circuit quickly enough in order to keep from losing charge off the capacitor. So, but we can play around with R and C and get to the point where you can sort of see the decay. Anyway, on that note, have a wonderful weekend. Today's Wednesday. Yeah. Don't forget, test next Wednesday, chapters 23 through 26. This is chapter 28.